This is my 10th video on multivariable calculus challenge problems. To this point, we've solved problems and used the computer program Mathematica to make animations of the geometric situations behind the problems. And that continues in this video, but I want to do something a little extra special in this video. And I wanted to actually have a physical prop. As you look over this problem, what kind of physical prop could we use? How about a spool of thread? So I said, honey, I asked my wife, honey, do we have any spools of thread around? And she said, yes, of course we do. And here is the spool of thread that I'm going to use to illustrate what's going on here in this problem. I tried doing it ahead of time with my fingers, and I'm kind of a fumble fingers person, so I wasn't able to really demonstrate this effectively with my fingers. So I was also here at work now and asking around, does anybody have any tweezers? And nobody did. I ended up going down to my friendly neighborhood chemistry professor and said, do you have tweezers? And he said, yes, we do, but we call them forceps. So here are the tweezers or forceps that I will use to demonstrate what's going on in this problem about the involute of a circle here, problem 29 in section 11.2 of Rogawski and Adams calculus book, but of course you can find similar problems in other calculus books. I did also a little research ahead of time, and looking into the future, we will be talking more generally about involutes and evolutes of curves. They are dual concepts, and they even have applications I saw online in general relativity. So really fancy applications of involutes and evolutes of curves, but we will do more down-to-earth applications. This spool of thread. Let's see if I can do this demonstration now. It's a little tricky, and of course impossible to do perfectly. So we want to make the spool of thread line up with this circle essentially, and grab the end of the thread and twist it until when it's essentially next to the spool, it's starting at the point, this point down here on this red curve, and now pulling this and keeping the thread taut, so not quite where I need to be here. Keeping the thread taut, we see it following the red curve pretty well. That's the idea of the involute of the circle. Keeping the thread taut means to keep it tight, no slack in it. Okay, you can see this is a pretty long video. This derivation does take a while if you want to completely understand it and completely explain it. So I would encourage you to maybe have some notes to take, a piece of paper and a pen or pencil. Pause the video, write down things that I write down, make drawings like this. This, by the way, is the only drawing that's actually in the book. I added this extra drawing because I would like extra confirmation in another case that these parametric equations are correct. So we keep the thread taut. The endpoint traces out a curve called the involute of a circle. See these figures below, that's the red curves. It is important to note that the line segment from P to Q, this line segment in this picture and this line segment in this picture has length r times theta, where r is the radius of the circle and theta is the angle that has been swept out so far. Why is that? Well, because you're keeping it taut, you can see as you do the unwinding that the length of this line is going to be the same as the length of this arc of the circle, whose angle is theta. Same kind of thing over here. This angle, theta, generates an arc of the circle, and this distance along this arc, because of how we're unwinding the thread, has to be equal to the length of thread that has been unwound. Why is it r theta? I should remark before explaining that theta must be in radians for this formula to work. This is in radians. Think about it in terms of proportionality. If you went all the way around the circle, theta would be 2 pi radians, and the length of the thread would be the circumference of the circle, 2 pi times r. If you go halfway around, theta is pi radians. R times theta would be pi times r, and that would be the length of half of the circumference of the circle. So you can think proportionally like that. The author is just wanting you to trust this formula, but I hope that makes some sense. Okay, so when theta is radians, r times theta is the length of this arc, which is the same as the length of the unspooled thread, the same as the length of the line segment from P to Q. show that C is parameterized by these equations here. Well, this one equation, C of theta, gives you the parametric curve, but each coordinate of C could be thought of as an equation. X equals r times, in parentheses, cos theta plus theta sine theta, and y equals r in parentheses times r times, in parentheses, sine theta minus theta cos theta. That derivation is going to take up the bulk of our time. We're not really doing a proof when we do that. It's not really a mathematical proof, it's a derivation. It's enough to convince most people, though we will do it in 2 cases. And think about it slightly differently in both cases, but see that we get the same final answer. We will also be finding the length of the involute as theta goes from 0 to 2 pi, which can also be thought of as distance traveled if it's a motion you're thinking about, if you're imagining the angle to not just be the angle that you see, but also time going by. That calculation actually is fairly simple, even though the equations are kind of complicated here. We will need the product rule, and it'll look a little messy at first, but it simplifies pretty nicely. So again, the main bulk is going to be taken up by doing this derivation. So we're about to start on that. For the sake of seeing things more clearly in these pictures, with things being kind of small, I'm going to zoom in. We'll start with the leftmost picture. Let's see, make sure this is focused. You're probably going to see it get light and dark from time to time as I move my hands. Hopefully that's not too much of a distraction. Okay, you see that the answers do involve cosines and sines, and that's a hint that you want to use right triangle trigonometry, which we will use here. Though, even if you didn't see those formulas ahead of time, but maybe just have the picture, I hope you would be thinking that you would still need to use right triangle trigonometry. You see a right angle there, you see an angle. Now the initial temptation might be to draw a line segment from the origin to the point P and get a right triangle that way. But it turns out that's not the best thing to do. The best thing to do is to initially find the coordinates of Q in terms of r and theta, and then use those coordinates to figure out the coordinates of P. By the way, I am abusing notation here. P represents this point, and I'm saying it equals its coordinates. Well, technically, points and coordinates are different things, but it's usually not too much of a problem to abuse notation like that, and that's going to be a common thing that I do. I'm going to do something similar with Q. Let's call its coordinates a comma b. And those are rectangular coordinates, by the way. And for this picture, if you draw a line straight down from Q to the x-axis, making a right angle here, and if the coordinates of Q are a comma b, then a does have to be the length of this side of this right triangle, and b does have to be the length of this side. And r, the radius of the circle, is also the length of the hypotenuse. Okay, so based on that, and thinking about good old SOHCAHTOA, you can get a and b in terms of r and theta pretty quickly. Focusing on SO and CA, sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. For this right triangle here, sine of this angle theta, which is this angle right here, opposite over hypotenuse, the opposite side has length b, the hypotenuse has length r. This is b over r. And therefore b is r sine theta. And the cosine of the angle is adjacent over hypotenuse. The length of the adjacent side is a. This is a over r, and therefore a is r cos theta. Those are the coordinates of Q. You also could have thought of those in terms of polar coordinates. If you use the transformation of polar coordinates, r and theta to x and y, so to speak, a and b in this case, these are the equations that polar coordinates gives you. All right, there's another good right triangle to draw in here, and that is to draw a horizontal line from P over to the red line here, making a right angle like that. Now, it might look initially like these two triangles are congruent, but they are not necessarily, actually. Remember, the line segment from P to Q has length r theta, not r. So even though these look like they could be the same length, or maybe this one's slightly longer, they are indeed, in general, different lengths. This is length r theta. So these triangles are not congruent unless theta happens to be 1 radian, which is about 57 degrees, I believe. But they are similar. They both have a right angle. And it does turn out, if you think about it, that this angle right there also has measure theta. These two angles here and here are congruent. These are similar triangles. Part of doing your showing, deriving in this problem, should be explaining that fact. Why are those two angles congruent? Well, they, if you think about them in relationship to this angle here, if you add this angle to this angle, or this angle to this angle, in either case, you've got to get pi over 2 radians, 90 degrees, right? Because the angles in any triangle all add up to pi radians, 180 degrees. You've got a right angle, so the remaining two angles have to add up to pi over 2 radians, 90 degrees. So these two have to add up to the same thing, and these two, being part of this right angle, have to add up to the same thing. And therefore, this angle and this angle must be the same. They have the same angle measure. So this angle can be labeled with a theta as well. And now I can apply right angle trigonometry to that right triangle. I can say sine of theta based on this other right triangle. Opposite or hypotenuse is this side divided by that side. Now I haven't labeled this side yet. Let's label that. Let's label this C. And let's label this side of the other triangle D. Based on that labeling, I can say sine theta is C over r theta. And therefore C is r theta sine theta. And the cosine of the angle adjacent of our hypotenuse is D over r theta, and therefore D itself is r times theta times cos theta. And that is starting to look pretty good, looking at what our answer is. How do we finish it here? Think geometrically here. For this picture, in this situation, the x-coordinate of P, the first coordinate, must be A plus C. A, B, C, and D here are all positive quantities. A plus C must give you x. What about y? Careful, it's not B plus D. B is the entire length here, which is the second coordinate of Q. But for this picture, at least, P is lower than Q, y is less than B. By how much? By D. Y is B minus D. Now plug in what A, B, C, and D are in terms of r and theta, and we're done with the derivation for this picture. A plus C is this plus this. Add those two things, you can factor out a common factor of r and get r. What's left? Cos theta plus theta sine theta. So the first coordinate of P is r times, in parentheses, cos theta plus theta sine theta, which is the exact same thing as what's up here. And the second coordinate is B minus D, this thing minus this thing. Factor out the common factor of r, and you're left with sine theta minus theta cos theta. That matches this. Okay? So that's a derivation based on this particular picture. But if your picture changes, like if it's the second picture, the derivation could actually be a little different. Now I'm still going to call in the second picture the coordinates of Q A comma B. However, keep in mind that if this is the situation, if this is the picture, A would have to be negative and B is positive here. I'm still going to call them A and B. You still could think in terms of polar coordinate equations. These actually are still valid. A comma B still does equal r cos theta comma r sine theta. Even when we're over in the second quadrant here, even when theta is between pi over 2 radians and pi radians, this is still true. Cosine of theta, cosine of such an angle would be negative. A is negative, cos theta is negative. Can still make that labeling though. So what's left is to help us figure out how Q is again related to P. I'm going to draw triangles that are essentially rotated and, well, at least with the second triangle, expanded versions of these triangles. I'm going to label the sides differently. Let me draw a horizontal line from Q over to the y-axis, making a right angle right there. And let me also draw a vertical line from P down to this line right here, making a right angle right there. Based on giving the coordinates of Q, the letters A comma B, and A is negative, technically speaking, the length of this side here is not A, but negative A, which is a positive quantity based on this labeling. The length of this side here is B. B is a positive number. I'm tempted to label the sides of this other triangle C and D, but I think I should label them differently. Let's call this side E and this side F. E is not the number E. It's not 2.71828. F is not a function, okay? I'm using these letters to represent these side lengths. As before, the length of this hypotenuse here is still r theta, but now theta is bigger than in this other picture, and so we get a longer hypotenuse. These triangles are definitely not congruent, but they are still similar. And now we're to what's the hardest part here. Let me label this angle with a different symbol that I haven't used so far. Oh, how about another Greek letter? Let's call it alpha. Alpha does not equal theta, but it's of course related to theta. Theta minus pi over 2 would equal alpha. Pi over 2 is 90 degrees. Just like before, where this angle and this angle were congruent, so this angle here with measure alpha and this angle here are going to be congruent. This angle is also going to have measure alpha. Okay? So I'm going to write E and F in terms of r, theta, and alpha. But then the hardest part is going to be relating that to just r and theta. Okay? So hang with me here. Once again, I use SOHCAHTOA. I can say, based on this bigger triangle here, I can say sine of alpha, this angle here, is opposite over hypotenuse E over r theta. And therefore E is r theta sine alpha. And I can say cosine of alpha is adjacent over hypotenuse F over r theta, and therefore F is r theta cos alpha. I can also say, based on this picture, that, let's use black here, that X for this picture is A, which is a negative number for this picture, plus the positive number F. A is a negative quantity that essentially brings you to the first coordinate of Q here. Adding on the positive quantity F gives you the first coordinate of P. X is A plus F, though A is a negative number. And that's going to then be A is r cos theta, and F right there is plus r theta cos alpha. But ultimately, the final hardest part is getting cos alpha in terms of either cosine or sine of theta. Hang with me here. Y is, second coordinate of Q is B. Length of this leg here as a positive quantity is E. Y is B plus E. B is R sine theta. And E is R theta sine alpha. So how do you get cosine of alpha and sine of alpha in terms of cosines or sines of theta? You could look up a trigonometric identity. We are going to use the fact that theta is, or alpha is theta minus pi over 2. But what if you don't have trig identities handy? Is there a way to figure it out? Well, you would still have to know what the graphs of the cosine and sine function look like. Let me draw the graph of the sine function first. Let's label this axis as theta. The graph of sine theta would look like this. It's periodic with period 2 pi. This is theta 0. This is theta's pi over 2 here where it reaches a peak. Comes back another intercept at theta equals pi. This is 3 pi over 2. This is 2 pi. That's the graph of sine of theta. What's the graph of sine of theta minus pi over 2? If you know about horizontal shifts, you would know that the graph of sine of theta minus pi over 2 takes this entire graph, shifts it to the right by pi over 2 units, and gives you a graph that looks like this. Now, if that's confusing to you, you're going to want to pause the video and think about it. It's taking the graph of sine theta and shifting it to the right by pi over 2 units to give you the graph of sine of theta minus pi over 2. And if you look at that, it's got symmetry with the cosine graph. It's the cosine graph reflected across the horizontal axis. And therefore this equals the opposite of the cosine of theta. So ultimately, sine of alpha can be replaced with negative cosine theta, which is what I would do right here. I'd replace that sine alpha with negative cos theta, and that would give me the y coordinate. I won't bother writing that down. Should I say it again? Sine alpha can be ultimately replaced with negative cosine theta. I can do that replacement right there. That's where the minus sign and the cosine theta comes into play. Let's also think about replacing cosine of alpha with something involving theta. Let me draw the graph of sine of theta and shift it to the right by pi over 2 units. So here's the graph of sine theta. Oops, I meant the graph of cosine theta. Here's the graph of cosine theta. If I shift that to the right by pi over 2 units, I get a graph that looks like this. And in fact, that graph, that new graph that I get, is the graph of the sine function. So this is illustrating that cosine of alpha, which is cosine of theta minus pi over 2, the graph of the cosine function shifted to the right by pi over 2 units is the same as the sine of theta. So up here, cosine of alpha gets replaced with sine theta, and I get this right there. I guess I will say this is sine theta, and this here is negative cosine theta. Okay, so that derives the equations based on this picture. And that's enough, okay? And in fact, probably for most professors, it would be enough just to think about this picture. That's enough of a derivation. You don't have to continue thinking about the third and fourth quadrants unless you really wanted to. That's all I want to do for the derivation. Now we're going to go on to finding the length of the involute as theta goes from 0 to 2 pi. And that calculation actually is the easiest part of this problem, though we will need the product rule if we're going to be a little careful about it here, as we should be. I've talked about how integrating the speed function gives you the distance traveled, which is the same as the arc length. And the speed function is the square root of the square of the derivative of this thing plus the square of the derivative of this thing. That is also the same as the length of the velocity vector. And again, we're not talking fully about vectors yet. In the last video, video number 9, I kind of also derived the integral of the speed giving the distance traveled in another way by thinking about Riemann sums. I would like to do one extra conceptual thing in this video, and thinking about finding the length, arc length, distance traveled by adding up elements of arc length. What is an element of arc length? We are still going to do the Mathematica, by the way, but I will keep that part of the video fairly short. And this is not too long either. I mean, what we did up here was definitely the longest part of the video, the bulk of the time here. What is an element of arc length? Well, traditionally it's called ds, symbolically. And what I'm about to explain is a very intuitive way of thinking about it. It's not fully rigorous. It is the way a scientist or engineer would think about it, usually. It's not fully rigorous math. It can be made rigorous by using something called non-standard analysis. But if you look up some books about non-standard analysis or look online, you will quickly see it's a pretty complicated subject. And so we are typically satisfied with taking an intuitive approach. And I tell this to my multivariable calculus students all the time, even my Calc 1 and Calc 2 students. It's okay in many situations in calculus to derive equations, especially involving integrals, intuitively by thinking in the way that I'm about to explain. So use your imagination. Imagine you've zoomed in on this curve super far. You've used a microscope, maybe an electron microscope, just to be extra dramatic about it. Zoom in really close, say to this spot here, until the curve looks straight. It looks like a line. Now, is it actually a line? Technically not. Technically, it's still got some curvature to it. But we imagine we've gone in so far that it basically is straight. Okay, this is non-rigorous talking. And call the length of that line segment ds. S is a traditional letter used for arc length. ds then represents a tiny arc length. Now I could draw a right triangle in here. And if I do so, and if I'm calling the length of the hypotenuse ds, it would make some intuitive sense to call the lengths of the sides dx and dy. And then relate ds to dx and dy with the Pythagorean formula. ds would be the square root of dx squared plus dy squared. Now comes the extra hand-wavy part. I'm waving my hands here, maybe too fast for you to see. This is the part that's really suspicious and non-rigorous. I am now going to relate these to the parameter theta, or if I was using t for time, I'd relate them to the parameter t. I'm going to do a manipulation that's going to be a bit fishy. I'm going to replace the square root of dx squared plus dy squared with the square root of dx d theta quantity squared times d theta squared plus dy d theta quantity squared times d theta squared. And then I'm going to factor the d theta squared out, take its square root, assume it's positive, and rewrite this as square root of dx d theta squared plus dy d theta squared, and have the d theta without a square outside the square root. Okay? So, if dx and dy and ds were just particular numbers based on this picture, and they were not infinitesimally small, certainly there's nothing wrong with this computation, thinking of these quantities as being lengths, and d theta as just being some other number. But we now make a transition to thinking of these things dx d theta and dy d theta as being derivatives. And that's actually ultimately the reason we use this kind of notation with the d's. It's going to relate to the Leibniz notation for the derivatives. And so then this quantity here becomes what you would then call maybe the speed, at least if theta was also the same as time. It would be the speed of motion as theta is increasing as time is going by. That would be what we've done in many other videos, is representing the speed. And you do integrate the speed to get the distance traveled. Or arc length, which is typically called s. But now with this approach, you think of the integral intuitively as just being adding. In the last video, again, we looked at Riemann sums, and Riemann sums approximate the integral, and that's all good and fine and more mathematical, you might say, than this approach. A little bit more rigorous. But this approach is quicker, maybe even more intuitive. Think of the integral sign as representing adding, and you might even write something like this. S equals the integral of ds. To find the total arc length, add up the little arc lengths. Think of the integral intuitively as being adding. But of course, to actually calculate this thing, you've got to write it as a definite integral. And in this case, it's going to go from 0 to 2 pi. Of the square root of dx d theta squared plus dy d theta squared. Integrate with respect to theta. Okay? Maybe I should put quotes around these equal signs. I'm not doing rigorous math when I do this derivation. I'm doing an intuitive derivation. That's what I'm doing. And that's okay. Okay? It's okay to try to get used to this kind of thing and not worry fully about the rigor, though it does lead to some situations in more complicated problems where you might feel unsure about whether what you're doing is right. And there are ways to try to confirm it. Maybe even making physical measurements, for example, to try to confirm your more theoretical equations. But for now, we're just satisfied with saying, okay, this makes intuitive sense and it does give us the right answer. Now this could be a complicated integral, and in fact in general it is. But in this problem, even with these equations being somewhat complicated, it's actually a fairly easy integral because the speed function simplifies very nicely. Let's finish the written part of the video by doing that, and then we'll go to the Mathematica, though again we'll keep the Mathematica part to hopefully a minute or two. So we've got to calculate dx d theta squared plus dy d theta squared. And what's going to happen is it's going to simplify very nicely down to something pretty simple. I'm going to factor the constant r out in front as a square, so I don't have to worry about differentiating, thinking about the r being there all the time. It is a constant. When you take the derivative, it just gets carried along for the ride. You are squaring it because you're squaring those derivatives, and that squared is going to be in both terms. You can factor it out. So I'm going to differentiate this thing, cos theta plus theta sine theta, square that, differentiate this thing, square that. Actually, before I square, I'm going to simplify pretty nicely. So dx d theta is going to be, first of all, the derivative of cosine theta is negative sine theta. Then I have to differentiate theta sine theta. I use the product rule. The derivative of theta is 1. That's the derivative of the first function times the second function, plus the first function times the derivative of the second. The derivative of sine theta is cos theta. And this all needs to get squared. So I just differentiated this thing up here in parentheses. Right there. Now I'm about to differentiate this thing. The derivative of sine theta is cos theta minus the derivative of theta cos theta, which I need the product rule for. The derivative of theta is 1 times the second function minus the first function, theta, times the derivative of the second, but the derivative of cosine theta is negative sine theta. By the way, it's important that theta is in radians here as well when we differentiate. So I get a plus theta sine theta, though actually that plus sign doesn't end up mattering because I square this thing. Before I square these things, you get cancellation. Negative sine theta cancels with sine theta. Cosine theta cancels with minus cosine theta. We're left with theta cos theta quantity squared and a theta sine theta quantity squared. I can factor the theta squared out. Use our favorite trigonometric identity that this always equals 1. So this simplifies to r squared theta squared. And therefore, I take its square root. The speed function is going to be r times theta. R is positive. I'm assuming for the sake of this situation that theta is positive as well. The speed is going to be r sine theta. And therefore S, the distance traveled or arc length, is the integral from 0 to 2 pi of r theta d theta. And that's a pretty easy integral to do. R theta squared over 2. Theta goes from 0 to 2 pi. And that gives you 4 pi squared r over 2, which simplifies to 2 pi squared times r. That is the arc length as theta goes from 0 to 2 pi. Could also note that we could have made the upper limit of the integral a variable, whatever variable you want to call it, maybe beta or something, and the arc length function, or distance traveled function, would have been r beta squared over 2 if beta is an arbitrary angle. So while the angle increases linearly, the arc length increases as the square of the angle is the point I'm trying to make by writing that. All right, now we're finished with the written part. Let's go to Mathematica. All right, now we're into the Mathematica portion of video number 10 on the involute of a circle. The goal here being to see the pictures and see the Mathematica code that generates an animation of the thread being unwound from the spool, though I did not try to actually make a spool in the picture. These are our functions. This is the x-coordinate as a function of theta. This is the y-coordinate. This is c, which is the point. I also added some vectors in here, velocity vector and acceleration vector, in terms of derivatives of position vector. Speed can be found by this. I'm not going to explain what this is. It's related to something called the dot product if you're interested in looking into that. Here's the code for the first static picture, right here, if you want to copy that down or take a picture of it or whatever. And I enter it to see the first static picture. The theta that I happen to pick here, the angle is 2 pi over 5 to get this picture. And I made the second picture by taking the angle to be 11 pi over 12. And here's what the code generates. It generates the second picture. As usual, I can make an animation now of the motion. Theta is the parameter represented by the letter b here actually. R is the radius of the circle, set to be 1 here initially. I let theta increase linearly over time. It effectively is time. And we see the red curve, the involute of the circle there. Also, you see vectors. The blue vector is the position vector. It points from the origin to the point, the end of the string as it moves, the thread. The red vector, red arrow, is the velocity vector. It's the derivative of the position vector. And the orange vector is the acceleration vector. It's the derivative or rate of change of the velocity vector. Note that the angle between the red and orange is always less than 90 degrees, so the red is always getting longer. You are always speeding up here with this motion. I can also change the size of the circle here. I get a different sized involute. And we can confirm symbolically the formula for the speed function does simplify to this, which can be simplified assuming r and theta are positive, as they are, to just r times theta, and then I could do an integral in Mathematica. But this, again, is such an easy integral that we don't need to bother. Okay? So once again, long video, but I hope you got a lot out of it.